All right, we are getting into this final week of this course, NPTEL course, on Advanced Reinforced Concrete Design. And in this module, we are going to discuss another important topic, which is analysis and design for two-way slabs. We have not discussed the design of one-way slabs or one-way continuous slabs, because that's going to be very similar to that of beam design that we have discussed. So, two-way slabs is a very important topic. We'll cover that in this module 10. And in this module, we are going to talk about overview of different types of slabs. And there are two popular methods that are commonly used for design of this slabs, at least for hand calculations, which is direct design method and equivalent frame method. And these methods are usually used to check what results that you're getting from your finite element analysis. Okay, so in this module, we will talk about the overview and what are the expected learning outcomes after the student under gone through this video. The student should be able to differentiate one-way and two-way slab and explain the moment distribution in one-way and two-way slab and explain the different types of slab system that we are going to see. And there's going to also be the effect of torsion, okay, especially for a slab supported on um, four sides, and if they are prevented from lifting up, then we need to put some additional reinforcement to take care of the torsion. And we'll briefly explain what is a code coefficient method for the design of slabs. Right. So let's get into this slabs. So slabs can be categorized as one-way slab or two-way slab depending upon their predominant directions of bending. Okay, so the definition for one-way slab is especially for, let's say, the slab is supported on all four sides through some beams. Then, if the ratio of longer to shorter side of the slab, if it is at least equal to 2, that means the longer to shorter side of the slab panel, if you divide, take the ratio, if it is going to be more than 2, then we say that the slab is going to bend predominantly in one direction. Then we say this as a one-way slab. So now you can ask me why exactly 2? That is an acceptable number. So it doesn't mean that if it is 1.99, it is going to be a two-way slab, and if it is going to be 2.01, it is going to be one-way slab. 2 is basically a boundary value that we use to differentiate between one-way and two-way slab. In fact, if it is going to be very close to 2, it is better to put reinforcement in both the direction. It's going to bend more like a two-way slab. So this is just a number to differentiate the when that demarcation between one-way slab and two-way slab is. Right. So let's say that when this ratio is more than 2, then under the action of your loads, the one-way slab is going to deflect in the short direction only. That means it's going to have a predominant curvature in the short direction, okay, in a cylindrical form. So therefore, the main reinforcement is placed in the shorter direction, okay. But if your ratio is less than 2, then you are going to have curvature in both the directions and you need to put reinforcement in both the directions. Though in one-way slab also, we put main reinforcement in the shorter direction. In the longer direction, we also provide with some nominal reinforcement to take care of shrinkage related issues to limit the cracking from shrinkage and temperature stresses. So one-way slab will have main reinforcement in the shorter direction. However, in the opposite direction or the orthogonal direction, we need to put some nominal reinforcement to take care of the shrinkage related crack. Now, so this is one example, okay. So if you see here, there is going to be a beam like this, and beam is going to be like this. So in this case, the beam is running along the column only in one direction, the other direction you don't have beams. So because in this case you have supports only on one side, doesn't matter what the L by S ratios is, this slab is actually going to bend like this, okay. So between the beams. Okay, so in this case, it doesn't matter what is the ratio of the panel. Okay, so usually the panel dimensions are taken from column to column like this. Okay, but in this case, because I have support is going to go only in one direction, which is this, right? Then it is basically bending in only one direction. It doesn't matter what the L by S ratio that you have because the support is like so. It is going to bend only between the supports like that. Now, when you have other case, let's say, for example, the figure that we are seeing here, you have slabs that are supported on beams, which are running along column lines. Okay, like this, you have a beam like this, you have a beam like this, a beam like this. You also have another secondary beam like this. Then you take the panel only this, and provided this middle beam is also quite substantial, then when you look at this ratios of longer span to the shorter directions, you will find that the longer span is much larger than the shorter span direction, right? Then in the ratio is going to be definitely more than 2. So the direction is going to be only along shorter direction like what we have seen here. So this is going to be predominantly bend in one direction, in the shorter direction. Doesn't mean that it's not going to bend in the other direction, but the curvature in the longer direction is going to be very small. So that is going to produce very small moment. So this is the way we differentiate between one-way bending and two-way bending of a slab. Now, so when the ratios, let's say if the panel is supported on beams on all four sides or walls on all four sides, if the ratio is less than 2, then it is called two-way slab, and the bending will take place in two directions in the dish form. So it is going to bend like a dish or a bowl, right? Accordingly, the main reinforcement is put in both the directions. Okay, so that's what we are seeing here. Let's say this is a slab panel that is rested on all four sides by some stiff beams. Okay, if that is the case, when you look at strips, let's look at strip number 1, strip number 2, and then strip number 3 and 4. Okay, so if you look at in this case, now the L1 by L2 is greater than 2, but it is less than 2. Okay, so if that is the case, so L1 is greater than L2, then L1 by L2 ratio, when you take it, we are finding that it is going to be less than 2. So the slab is going to have bending in both the directions, like the one that you have seen here. Okay, so it's going to bend like a bowl with deflections going in both the directions, right? So if that is the case, when I look at strip 1 and 2, when you have a strip 2 which is very close to that of support, it's not going to have a much curvature. So, and you know that the moment is always proportional to the curvature of the bending, right? M is equal to A into d square y by dx square in your simple bending theory. So higher the curvature of the bending in that direction, higher will be the bending, right? So if you look at the strip 1 and 2, because strip 2 is very close to that of support, you're going to have less curvature and your moment is going to be less. But strip 1 is away from the support, so it's going to have a larger curvature, then you're going to have larger moment in strip 1. Similarly, in strip 4 also, you're going to have some moment, okay, but that moment is also going to be there. So in this way, the moment is proportional to the curvature of the bending, okay. So now let's look at what happens. In one-way slab action, as we have discussed, let's say this is one supported region, this is one supported region, right? So we're looking at this and this one, right? So it's simply supported only on this edge, and the other two edges are unsupported. So again, as we have discussed, if you take this small strip like this, right, you can analyze this like a one-way strip. So that's why for one-way slab, what we do is we take a strip of 1 meter width, and then you do it just like your beam, one-way continuous beam or a simply supported beam. So then this is basically your one-way slab action. Now, in the same way, let's say now the panel is rested on all four sides. Then, as we have discussed, the loads will get transferred in this form. Okay, so when you draw like this, when you draw like this, okay, so in this way, whatever that area that is there close to this, so whatever the area that is load is applied on this trapezoid will go to this uh, support here, right? In the same way, this area is going to be supported on this support. So in this way, the loads are getting transferred, and the slab is going to bend in both the direction, and it is going to have this kind of deflection contours like what is shown here. Okay, so the deflection contour is going to be like this. So what we have seen, you're going to have high deflection, then the deflection will keep reducing. Okay, so this is what the deflection contour is. Okay, And as you go to the support, the deflections are going to be zero. Now, for the same slab, if it is going to be having a long aspect ratio, that means longer span to shorter span is going to be higher than 2, for example. The same slab, even if it is supported on all four sides, you will find that again in this direction also you will have some bending. Okay, but that bending is going to be very, very small compared to that of the bending that happens in the shorter direction. That means that the slab is basically bending more in the shorter direction, predominantly bending in one direction. In the other direction, your curvature is going to be very small, so the bending moment is also going to be very, very small. So, or in other words, this my in the longer direction is going to be much, much smaller than of your shorter direction bending moment. Okay, so these are the way that we distinguish between one-way slab and two-way slab. Now let's quickly look at what are the various slab systems that are prevalent in practice. So this is the one nice system. We call this as a pan joist floor system. Okay. In this pan joist floor system, you have this small joist. Okay. And usually they are spaced from half a meter to 0.75 meter. And the depth of this joist is usually from 0.25 to zero point 0.5 meter. And this joist also will have a slope, usually in the ratio of 1 is to 12, 1 horizontal to 12 vertical. So it's going to have a very small slope also. This kind of a system is called as one-way joist or pan joist floor system, and you can see that now. Of course, this some of these at the edges you will have girders like this, the one that we are seeing here. If you have a column support like this, so this is your column and this is your column, right? So this is your column and this is your column. Here you will have a long girder, okay, which is going like this. But similarly, along the column line you will have long girders. But however, between the column lines, between those girders that are going along the column lines, now you will have this kind of small joist which will be running and transferring the load to the main girders which is running along the column line, right? And because of that, the slab now it's going to bend between this short direction. Okay, so the predominant direction of the bending is for the slab is going to be only like this. Okay, so these, because now I have created a support and this direction is maximum, let's say 0.75 meter, and you will find that on the other direction definitely the length is going to be much longer, because that's going to be distance between the two column lines, right? So it's going to be much, it may be in the order of 4 meters, 5 meters, 6 meters. So you will find that it's going to predominantly bend in the shorter direction, the slab between the joist. Okay, so this type of slab is also called as a ribbed slab, and usually it consists of a floor slab with 50 to 100 mm thick. Usually we put about 100 mm thick or so, and then it is supported by small ribs or joist. So these are also called as ribs or joist. Okay, the ribs are usually tapered and uniformly spaced at a distance that does not exceed 0.75 meter, as we have discussed. And these ribs again, they go and get supported on girders that runs between the columns. So in some ribbed slabs, the space between the ribs may be filled with permanent pillars to produce horizontal slabs of it. So what does that mean? So basically what we are telling you is the space between the joists, you can create some kind of a false ceiling like this. Okay, so and you can, so that you can create a horizontal slab solid. That is just purely from architectural or aesthetic reasons, but it is not really mandatory to fill the space. Now let's look at it. So again, floor joist, you can have systems like this. Now, as we have discussed, you have um, a floor joist type. So these small lines that what we are seeing here, these are basically your joist. Okay. Now, what is the span? The slab is going to basically run between these joists. Okay. So this is the direction of your slab. Anyway, bending. Now, these slabs, these joists have to be in turn supported by girders which runs along the column line. Now you can see floor joist one-way slab with only girders on only one side. So what does it mean? Now in the for this floor joist, you have girders only on this direction. Okay. Though you have some at certain after certain several column spacing, you have something, but predominantly you have girders are running only in one direction. Okay, so the joists are all supported on girders only in one side. Now you can also have another scenario. Okay, you can have floor joist one-way slab with girders on both sides. So if you see here this case, everywhere I have two sides. Okay, so it's basically it's resting on all two sides, and every between every column lines you have girders. Okay, so in this way, this kind of system I can reduce the thickness of the slab as well as the thickness of the joist, because now I have girders running along column lines on all the four sides. Okay, so this is another type. Now why this is called as 2D lateral frames? Okay, so if it's a moment resisting frame, that is considered, and if they're quite rigid, and if they're going to take part in lateral load resistance, then we call such kind of frames as lateral load resistance. Sometimes the intermediate ones also can be designed either only for gravity purpose or lateral beams. So how do you design whether it is a gravity or lateral? It all depends upon the dimensions of the beams and columns that are there, right? So in this case, when you have a floor joist one-way slab with girders on both sides, usually these all these frames are designed for lateral loads. They are quite stocky in their sizes. That means the girders which run along the column lines are going to be quite stocky. They're going to be bigger, and the columns that are supporting is also going to be bigger. So they're going to act like a moment resisting frame in both the directions. Now let's get into the two-way slabs. Okay, so two-way slabs, the first variety is basically flat plate or simple slabs. As the name says, the slab is directly rested on columns like this. So, and you don't have anything like a drop panel or a column capital. So such kind of systems are called flat plates. So there is a difference between flat slab and flat plate. Flat plate, your slab is directly supported on the columns without any drop panel or column capital. Nowadays, in a commercial building, these kind of systems are getting more and more popular, and these are designed to take care of only gravity loads. For lateral loads, anyway, I need to have some other shear wall system or some kind of a moment resting frame at other locations along the periphery of the building to take care of it. Right? So it is a two-way slab with no supporting beams, and it is supported directly on columns. So the slab has smooth under surfaces without column capitals or drop panels. So the moment your slab is having drop panel and column capital, we call them as flat slabs. But if you don't have a drop panel and column capital, we call them as flat plate. And because it is directly supported on a column, and you find that if you have a thin paper that is supported on a pencil, if you push it, the pencil is going to go through the paper, right? So that's called punching shear. And because these slab panels are directly resting on the columns, they are usually suited for very light loads associated with apartment construction, and maximum span is actually between 4.5 to 6 meters. As we have discussed, it is limited by their punching shear capacity. Punching shear is also called as two-way shear. Okay, it's not the typical one-way shear check that we do it in beams, right? These elements are going to shear in two-way shear, and around the column, if you want to support it for a longer span or a longer load, we need to, when you have a heavy load or large spans, okay, so this system will become uneconomical because you will end up providing more thick plates, and it may not be uneconomical, and deflection also will become excessive the moment your span is going to be higher, then the deflection is also going to become excessive. Okay. Now let's look at flat slabs. As we have discussed again already, flat slabs will have drop panel, okay, that what we are seeing here, drop panel, and also column capital. Both of them will be there. Now that I'm thickening the column around the slab where it is getting joined, then I can go for slightly a longer span from 6 to 9 meters, and this slab also can resist more loads than your flat plate systems. And you can see this is appropriate for heavier loads encountered in office or industrial buildings with maximum span of 6 to 9 meters. As the depth of the slab is relatively small, its capacity to transfer loads into columns by shear is often low. Okay, this is again because we don't have beams. Though we have improved it from flat plate, still the thickness around the column is only from drop panel and column capital. And most failures of flat plates are initiated by overstressing shear at columns, and they are termed as punching shear failures. Okay. So that is the reason. So to reduce, either you can have slab only with drop panel or slab with only column capital, or you can have a combination also like the one that we see. Okay. First slab will have a drop panel, and then drop panel will change to column capital and then to the column. So this way you slightly increase the area around the column. So these systems are very quite attractive, especially if you want to get rid of the beams, and so let's say that there is a height limitation. Now that you have removed the beams and you are directly transferring the load from the slabs to the columns, then every floor, let's say I'm doing some 400 mm 500 mm, then you can see the amount of savings in materials. Plus, if there is a height limitations, I can go for additional floors for all the depth of the beam that we have saved. Okay, these are all some of the advantages, but the disadvantages, it can undergo punching shear failure. We need to be careful, and also the lateral load resistance of such kind of systems is not going to be high, and they are predominantly gravity load resisting system, so it cannot help in transferring the lateral loads. So this is one of the things. Now, flat plate and flat slab are usually combined with post tension post tennings. So in post tension system, we run the post tensioning cables inside the thickness of the slab, and then we stress them. So these kind of system, when you put the slab under pre-stress, then I can go for a very long span. So that is a big advantage, and the shear resistance is also going to improve. So those are the kind of system now very commonly adopted in commercial buildings. And if you do not have post tensioning, you lose the effect of your pre-stressing, and then your spans will be limited, and the load what you're going to transfer is also going to be limited. That is the reason usually flat plates and flat slabs are done with post tensioning. There, with a very thin slab, still I can go for a longer span, and also the pre-stressing is going to help in improving the deflection and also going to increase your shear capacity. Right. So the next one is for a regular RC slab construction or cast in place concrete construction. You have slabs are supported on beams like this on two directions. Okay, so you have beams which are running along the column lines, and the slab that what you are going to design is going to be either two-way or one-way, depending upon the ratio of longer length of the panel to the shorter length of the panel. So beams are actually provide moment interaction with the columns, especially in moment resting frames are used to resist lateral. So these, the moment you have beams and columns, that will form a moment resting frame that will help in uh, transferring your lateral loads to foundation safely. Right. So there's another variety which is called waffle slab. Again, another two-way slab. And these waffle slab, as the name says, it looks like a waffle that we eat with all the small holes. Okay. And the waffle slab is capable of providing the largest spans for conventional concrete floor systems with maximum from 7.5 to 12 meter span. Also, we can construct using this waffle slab. But this construction of this raffle slab, you need to have these forms. When you pour concrete, you need to create this all the small openings, right? So that is a challenge. So you need to have a good form work to create exactly the same small holes. Okay, so and you can have different types of varieties, because again those waffle slabs are basically what is it we have created. We have created this joist, a small joist in both the directions. In addition to that, we can also thicken this area around the column. Okay, so this kind of a thickening we can do, like this is what you said. So you thicken the slab wherever you have columns. In that way, punching shear will be the punching shear failure probability can be reduced. Or one more way is each running along the column line, I can create a small band slab. So what is the meaning of band slab? The thickness you will keep it as same as that of your the small ribs that are running in the two directions, but the width I can increase it, again, that is going to help in reducing the pinching. So basically, you have created a shallow beam that is running along the column lines. Okay. So in this waffle slab construction, it consists of orthogonal sets of ribs with solid parts at the columns, and the ribs are actually created using fiberglass or metal dome forms. Okay. As I've said, you have to put this formwork and pour concrete and take the formwork out. Then only you create these ribs. And these ribs are usually zero point 0.6 to zero point 0.9 meter on center, and the shear is transferred to the columns by using beams or shear heads. Okay, so this is what we say there, shear head or thicker slab. This is called shear head. Okay, or this kind of a band slab we can put. Okay, the only again challenge is to have these kind of fiberglass or metal dome formwork to create this short ribs which runs along two directions. Now, edge supported rib slab. So, one more variety is you can have edge supported rib slab. So, it is similar to waffle slab, but in addition to that, I'm also going to have beams that are running along column. So, so in this way, what I can do, I can go for spans, higher spans from 10 to 15 meter span also I can. So, again, how do we create all this small waffle like kind of shape? You need to create a former. You put the formwork and pour concrete and take away the formwork. So then you create these ribs which runs along the beams, between the beams in two directions. Right? Okay. So now let's talk about, so we have talked about one-way slab and two-way slab and what are the various types of two-way slab that exist. Now, in two-way slabs can be subjected to torsion. So let us see what happens. So as we've seen, for the slab that is supported on, let's say, all four sides, if you see the deflection contour, and this is for uniformly distributed slab. So you're going to have higher deflection, and then the deflection contour is going to keep reducing, right? So if I take the small element right at the corner, if you look at the kind of moments that are going to have, you're going to have moment if you use your right hand rule. So you'll find that, okay, so you're going to have moment like this that is going to be acting. Okay, so this is your moment. Because if you say right hand rule, you're going to have bending moment, let's say about this axis and about this axis. Let's say this is y and x. Okay, so it is mx and you're going to have my. In addition to that, you're also going to have twisting moment. Now, this is similar to a stress element that is subjected to normal stresses and shear stresses. In the same way, instead of normal stresses and shear stresses, you look at it like this element is subjected to bending moment about both axes. In addition to that, it is also subjected to twisting moment. So, I can convert them into principal bending moment like what we do it in Mohr circle analysis, right? So for an element that is subjected to biaxial stresses, I can convert them into uniaxial principal stresses, right? So in the same way, for any element that is subjected to bending moment about both the axes and twisting moment, I can convert them into principal bending moments like this. So this is how it is going to be like this. So if you look at your principal bending moments, M1 and M2, and for the corner element like this, it is going to have both positive and negative moments that will be creating. So, and this is the distribution of your M2 and M1. One will be positive, one will be negative. Okay, if I take it along the diagonal for a simply supported square slab, and this is the way M1 and M2, these are principal moments, variations will be along the diagonal. Now, because of this, what will happen is I am going to develop some cracks which are going to be like this. Okay, you're going to have cracks like this. These are red colors, are basically that's going to come on the top of the panel, and then you have blue color cracks like this. These are going to come at the bottom. Okay, so these are the potential cracks. So both top and bottom of the slab at the corners are going to have cracking like this. And we know to prevent the cracking, I need to put reinforcement which is going to be perpendicular to the direction of the crack. So you'll find that now what kind of reinforcement that we need to put at the top, the reinforcement has to be perpendicular to the crack. So that is the reason we have this is your reinforcement, okay, which is going to be perpendicular to this red color crack. Now at the bottom, we are going to have this blue color cracks So I need to put reinforcement which are perpendicular to this blue color cracks or along this direction, right? So in this way, we put some corner reinforcement, especially when these slab panels are prevented from lifting up, this cracking will happen. So always, if you are preventing some rotations and deformation, you develop reactions, right? So if this panel is restrained from lifting up, and you will develop these principal moments and this crack. So that's why in the corners of the slabs, usually we put ideally, we need to put reinforcement at an angle, but it is very difficult to execute it in the field. So what we do is we put reinforcement like this in a simple grid. Okay, both top and bottom. Okay, so orthogonal layers at the top, both top and bottom, you put reinforcement like this at 0 or 90. So this will produce only when you are preventing these corners from lifting up, as we have said, because these elements are subjected to both twisting moment and bending moment. Because to satisfy the deformation compatibility, these corners will lift up like this. Okay. So now that I'm preventing this lifting up, so because of that, I'm going to develop cracking, and that cracking has to be arrested by providing some reinforcement in this form. Okay. So that's what we do.